Okay, hello geometry students. This is some notes that I've recorded on the smartboard for some of our new content that we were allowed to start posting. So I know that the circle chapter is pretty important and there's quite a few circles on the ACT test. So I hope that some of you guys are taking a look at these and looking at some of these worksheets and stuff that are being posted. So this is section 10.1. It's properties of tangents. So I'm gonna go through the study guide just like I would in class on the smartboard, fill in the blanks, do the practice problems, and we're gonna do some practice problems from the practice A worksheet, just like we would in class. And then I will post both the study guide and the practice A worksheet blank so you can work on it on your own. Not taking a grade right now, but hopefully some of you guys will use this. So 10.1, we're talking about circles in this chapter. So this first part of our vocabulary is all about circle stuff. Most of these you'll probably know or recognize. I mean, I think we all know what a center of a circle is and radius and diameter and that kind of thing. Some of the new ones probably brand new to you. So let's start in here. A circle is a set of all points in a plane that are equidistant from a given point called the center of a circle. So if I have a center right here and I draw a circle around it, okay, every point, all of these coming out, kind of like spokes on a wheel, are all equidistant from the center to the outside of the circle, okay? A radius is a segment whose endpoints are the center and any point on the circle. So obviously, this is a radius, okay, from the center to the point on the edge of the circle. That's our radius. A chord. Now, a chord is a segment whose endpoints are on a circle. So a chord, let me draw a new circle here. A chord is going to be endpoint on both endpoints on a circle. So this is a chord. Now notice a chord can be anywhere in a circle. It could be there, it could be there, it doesn't matter, just has to have its endpoints on the circle itself. Those are chords. Okay, now a diameter is a special chord that does go through the center, which we are all aware that a diameter is twice a radius. Okay, so a diameter is a special chord, okay, that doesn't just go anywhere, it has to go through the center of the circle, okay? A secant, now, a secant is close to a chord, but it also can be a, well, it is a line that intersects a circle in 2 points. So let me kind of point out the difference here. A chord is a segment, okay? A secant is a line that intersects a circle in 2 points. So this would be a secant. Okay, a secant is a line that goes through a circle and intersects it in 2 points. Okay, so the difference between a chord and a secant. A chord is a segment, a secant is a line. Okay, so big difference. Now, in particular, a tangent is a line in the plane of a circle that intersects the circle in exactly 1 point. Now I'm going to scroll down here a little bit because I'm going to have to draw a new circle here. So if we have a circle, I should probably use my circle tool to get a really nice pretty one. A tangent is a line in the plane of a circle that intersects the circle in exactly 1 point, the point of tangency. So the point of tangency, if I've got a line here that just touches my circle in 1 point, that's the only point it touches the circle on, that's the point of tangency. Okay, and this is my tangent line. Okay, now, tangent lines, again, only touch the point in one spot. Secant goes through a circle and intersects it in 2 spots. A chord is a segment that the endpoints lie on the edge of the circle. Okay, Okay, so theorem one, we've got a couple of theorems here about tangents. So theorem one, in a plane, a line is tangent to a circle if and only if, remember that, if and only if means it is biconditional, it goes both directions. If and only if the line is perpendicular to a radius of the circle at its endpoint on the circle. So what that means is if I have a radius here, okay, this theorem one is telling me that a radius that goes from the center to the point of tangency will be perpendicular. It has to be perpendicular to that tangent line. Okay, so the radius must be perpendicular to the tangent line. So tangent is perpendicular to radius at point of tangency. Okay, that's what that's telling us. The tangent line is perpendicular to the radius at point of tangency. Now, theorem two, tangent segments from a common external point are congruent. So what this is telling me is if I have a point out here somewhere in space, doesn't matter where it is, if I then draw a line from that point to my circle, okay, so it's going to cross here. So here's one line. Here's another line. Let's see if I can make this pretty. Okay, I can't even seem to touch the circle. I'm going to fudge it a little bit here. Okay, if I've got two lines that go through some common external point, okay, what this one is telling me is that the segments from here to here, from here to here, from here to here, these are congruent. Okay, so from the common external point to the points of tangency, the two segments are congruent. Now again, we're just talking segments. Okay, so let me label these. If I called this point A, B, and C, I would say that segment AB is congruent to segment AC. Obviously, we can't say lines are congruent, they go on forever, but those segments, okay, so imagine that I drew my purple line there and it was actually touching the circle. Those are congruent, okay? So that kind of takes us through our vocab for this whole section. Let's look down at some of these examples now. Example one, identify special segments and lines. So tell whether the line, ray, or segment is best described as radius, chord, diameter, secant, or tangent of circle P. Now notice this symbol here. That's our symbol for circle. Okay, this little circle with a dot in the middle. So segment RT. Well, segment RT obviously is a diameter because it's a chord and it goes through the center P. Okay, WT. WT, notice that's a ray. Okay, WT, so we're talking about this right here. Okay, WT is a tangent ray because it is contained in the line that intersects the circle in only one point. So the point of tangency then is point T. Okay, so it is a tangent ray. Technically, tangents can be segments, rays, or lines. Okay, so tangent ray. PT, segment PT is a radius because P is at the center. So PT here is a radius. P is at the center and T is a point on the circle. And line RQ. Line RQ is a secant. RQ is this line, again, with arrows on either side. Okay, it is a secant because it is a line that intersects the circle in 2 points. Now, if we said segment RQ, Segment RQ would be a chord. Okay, but line RQ is a secant. I just want to point out the difference to you guys again. Okay, segments with the endpoints on the circle are chords. Secant is a line that goes all the way through. Okay, let's go down to some of the practice problems. So in the diagram in example 1, I guess I need to keep it up there. What word best describes QR? Kind of already did that. I didn't realize. And PR. So first of all, QR we just talked about. Okay, QR we just talked about was a chord, right? Same thing as a secant, only it's a segment. Okay, so QR is a chord. PR, what is PR? Okay, PR from the center to a point on the outside would have to be a radius. I think we can all see that. Okay, QR is a chord, PR is a radius. Using the diagram in example 1, name a tangent. Now, I guess if they just said tangent, kind of the default is usually a line, but the only line that has a single point that intersects with the circle is that we have several different ways we could name it, but I would probably name it line XW. Okay, and point T would be the point of tangency. Okay, point T is the point of tangency. Let me just put that underneath. Okay. All right, let's go to the next page. Now, find the lengths and circles in a coordinate plane. So let's look at this example 2 here that they have for us. Use the diagram to find the given lengths. And you can see, I think this is pretty self-explanatory. The diameter of circle P, here's circle P, okay? Its diameter, notice first of all, the blocks are counting by 4. So remember, diameter is all the way through, it's gonna be 8. Okay, the diameter of circle Q. Circle Q is the big one, okay, because when we name a circle, we always name it by its center. So circle Q, the diameter is 16. We go 4, 8, 12, 16, all the way through. That was a crooked diameter, but you get the idea. Letter C there, the radius of circle P is 4 units. Well, obviously, if the diameter is 8, then the radius is going to be 4. And then the radius of Q is 8 units. Once again, if the diameter is 16, the radius is going to be half of that. Your diameter always equals 2 times the radius. Okay, always. Okay, now let's talk about common tangents. It says tell how many common tangents the circles have and draw them. Now, I'm intentionally kind of putting the answer right below that you can see. Common tangent, if the circles overlap, you're only going to have 2 like they do here. You're going to have one on top and one on bottom. There's nowhere else that you could draw a line that's going to hit a point of tangency on both circles. Okay. Part B there, if you have 2 circles that don't intersect at all, okay, you could have up 4 here. You could have one on top, one on bottom, just like we did in part A, but then you can also kind of have these sloped diagonal lines kind of here in the middle, okay, where they just touch a point on each circle. Okay, now, number C, where you have a circle inscribed in another circle and the circles only touch in one point. Obviously, this point right here would be your point of tangency, and that would be your tangent line. You're only going to have one of them. Okay, so now the other thing here on example 4 is we are verifying a tangent to a circle. Now, if you remember back in theorem 1, it says in a plane, a line is tangent to a circle if and only if the line is perpendicular to a radius of the circle at its endpoint on the circle. So we're going to be using Pythagorean's theorem. Okay, so we're supposed to show that BC is tangent to A. We're supposed to show that this is tangent to circle A. Well, the point of tangency would be point B, and if we're supposed to show its tangent, then we need to prove that this is perpendicular. Okay, to prove its tangent, we need to show that the radius is perpendicular to the tangent line, or in this case, the tangent segment. Okay, so that's what they're saying here. We need to show that these two things are perpendicular, so Pythagorean's theorem. Okay, you'll notice, if you remember, one of our Pythagorean triples was a 3, 4, 5 triangle. This is a 6, 8, 10. Okay, so if you remember, one of our Pythagorean triples, again, was a 3, 4, 5. Okay, that's a perfect right triangle, Pythagorean triple. So we have a multiple of that here with 6, 8, and 10. Okay, so 6 squared plus 8 squared does equal 10 squared, so it is a right triangle. That's what they're proving there. Now, let's go down here and look at number 3. So we need to use that diagram. It says in example 2 to find the diameter of radius, to find the diameter and radius of circle R and circle S. Now, back up here, circle R, it looks to me, so let's look at circle R here. This is circle R. Now, this is down here at what, 4, 8, 12, 16. So this is down here at like 16, 0. And then it looks like it goes up, and it looks like it's halfway between the 8 and the 12. So let's say 10. Okay, so it looks to me like circle R has diameter 10. Okay, so let me scroll back down here. Circle R has diameter equals 10, and that means the radius equals what? It's got to equal half that. It's got to be 5. So now let's go back up to circle S. Circle S. This would be my circle S. Again, it looks like it goes halfway between 4 and 8, so that would be maybe 6 since we're counting by 4s here. So circle S has diameter 6, so its radius would have to be 3. So circle S, diameter is 6, radius is 3. Okay. Now, let's look at these last ones. Tell how many common tangents the circles have and draw them. First of all, number 4, we did one like it right above. If you have 2, well, actually, no, we haven't done one like this. I apologize. 2 circles that are not concentric, they're not like inside each other, but they're right next to each other and touch at a point. What you've got here is you're going to have a point of tangency here. You're going to have a point of tangency here, if I could get it to actually touch. And because they touch at one point, I could also have a vertical line through there, and they could touch right there. That would have 3 common tangents. Okay? One on the outside, kind of top and bottom, and then one right down vertically through the one point of tangency that they touch. Number 5, is there any way to draw a tangent to both circles? And that would be a big fat no. Okay, there are 0 tangents. All right, I circled my 0 and now it looks kind of like the picture. So no tangents. Okay. I can't get to the inside circle to get a tangent without it becoming like a secant to the bigger outside circle. Okay. Number 6, if I have 2 circles and they're concentric, one's inside the other, and they touch at one point, I am only going to have one tangent that skims the both of them at their point of tangency. So that's just going to be 1. Okay, and I think we did have that example up above. Okay, now, number 7, using the diagram in example 4, is BD, let me scroll down just a little bit, is segment BD tangent to circle A? Okay, so segment BD, first of all, we're looking at this segment and we're trying to ask ourselves if it's a tangent to circle A. So once again, I need to check to see if this is perpendicular. Okay, so I need to check if BD is perpendicular to AB. Okay, need to check that. So in order to check perpendicular, I'm Pythagorean's theorem. So when I go to check that, I am checking if 8 squared, I hit one of my dead spots on my board. So 8 squared plus 15 squared, if I take the square root of that, does that equal 17? Okay, well, if we do a little math here, okay, if you poke that in your calculator, I can tell you, yes, it does. Okay, and again, all you have to do, or you could say, 8 squared plus 15 squared, does it equal 17 squared? Either one of those works. Okay, but again, if you poke that in your calculator, square root of 8 squared plus 15 squared, you do get 17. If you remember, that is one of our Pythagorean triples as well. Okay, is an 8, 15, 17, kind of like a 3, 4, 5 that we talked about earlier. There's also like a 7, 24, 25. There's several Pythagorean triples. Okay, now let's move on then. This concludes the notes part from the study guide. Let's move on to practice A and do a few of these together. Okay, so match the notation with the term that best describes it. Okay, point D. So if I'm looking at number 1 here, point D, first thing that jumps out at me there, it's got to be a point of tangency. Okay, got to be a point of tangency. And again, do not draw spaghetti lines like we're in kindergarten. Line FH. Okay, line FH. If I look here at FH, this line right here, okay, notice it hits there and it hits there, and I know those are tangent because they have them marked perpendicular. So how would I label the line FH? It's a tangent, but more than that, it is a common, what they would probably say, internal tangent. Okay, a common internal tangent. Now, why would we call it an internal versus an external? Because it went down through the middle, if you will, of or between the two circles. So this would be a G. Okay, common internal tangent. So again, what that means is between the circles. Okay. All right, so that's all you have to do on that part. The next part, use the diagram at the right. What are the diameter and radius of circle A, diameter and radius of circle B? I think you can do that. Describe the intersection of the two circles. Intersection right here, where they meet. The intersection would simply be a point, okay? And it is the point, what? What it is, let's see, 1, 2, 3, 4, 5, 2. The point 5, 2 is their intersection. Now, describe all the common tangents of the two circles. Now, this is the case where two circles intersect at one point. I would have a common tangent up here. That would be the horizontal line y equals 4. I would have a common tangent down here. That would be the line y equals 0. And then I would also have a common tangent that went right down through the center of them that hit that one tangent point. That would be the equation of my line x equals 5. Okay, so describe the all common tangents. There'd be 3. I would just put lines y equal 4, y equals 0, and x equals 5. Those would be my common tangents. Okay, now on this next part, it says draw a diameter AB. Okay, now remember, a diameter is a chord that goes through the center, so you can draw it anywhere. Okay, I'm just going to draw it straight across. But then I need to label my points here. This would be point A, this would be point B. Okay, so then draw a tangent line CB. Well, a tangent line, they want us to use the same point B. So a tangent line would be like here, and I would label some other point on that line C. So now I have a tangent line CB. We'll then draw a chord DB. This will be the last one I do. So again, they want you to use this B point and draw a different chord anywhere on the circle and label its endpoint D. Okay, and that's what you're doing. Okay, you can keep, you just have 2 more to do. So tell how many common tangents the circles have and draw them. Again, let's do number 20 here. I would say it has 4. You could do 1 here on the left, you could do 1 here on the right, and you could do a couple of internal ones if I can get my slope correct. You can do 1 like this and 1 like this. So it has a total of 4. Okay, 4 common tangents. Let's go to the next page. Draw 2 circles with the given number of common tangents. Let's do 22, where it has 2. So if I'm going to draw circles that have 2 common tangents, those are going to have to be overlapping circles, okay, that are then just going to have tangents on top and tangents on bottom. If they're overlapping, we can't have any internal tangents because we don't have any space between the 2 circles. Okay. The next part in the diagram, BC is a radius of circle C. Determine whether AB is tangent to circle C. Explain your reasoning. Well, right off the bat here on number 24, I would say yes, because that's my B/C. CB is perpendicular to BA. Okay, and we know that by that theorem 1, that we have a tangent if the point is perpendicular to the radius at that same point. Okay. 25. Is that a tangent? Well, we need to check to see if AB, again, is perpendicular to BC. Well, we have a 3, 4, 5 triangle. Does 3 squared plus 4 squared equal 5 squared? Yes. That is one of our Pythagorean triples, a 3, 4, 5 triangle. So that's a big fat yes. Okay, and you can do the next one. In the diagram, AB is tangent to circle C at point B. Find the radius. Now, this is a little different ballgame. On 27, again, we're going to use Pythagorean's theorem, but it's going to get a little different. So look at my diagram here on 27. So if I use Pythagorean's theorem, we're going to have 4 squared plus r squared equals, now here this is r, okay, this is 2. So my whole hypotenuse is going to be 2 plus r squared. You guys with me? Okay, so I have to prove that 4 squared, or I have to solve for r actually, if 4 squared plus r squared equals 2 plus r squared. So let me keep going with this then. I've got 16 plus r squared equals 4 plus 4r plus r squared. Now, let me make a note here. This right here has to be FOILed out. You have to FOIL that out. That's where this came from. Okay? You're literally multiplying 2 plus r times 2 plus r. So 2 plus r times 2 plus r is 4 plus 4r plus r squared. Now, let me keep going with the solving here. My r squareds are going to cancel. So I've got 16 equals 4 plus 4r. Subtract the 16, 12 equals 4r. So r equals 3. So this, my r equals 3. Again, it's a 3, 4, 5 triangle. Okay, 3, 4, 5 triangle. So you need to do the same thing with 28 and 29. Now, 30 through 32. JK is tangent to circle L at K, and JM is tangent to circle L at M. Find the value of X. If you remember back in the vocab section of the study guide, our theorem 2 stated that tangent segments from a common external point are congruent. Tangent segments from a common external point are congruent. So what that tells us is that that has to equal that. So X equals 22. These are easy enough. Okay, so again, over here, this is congruent to this. So 5x minus 4 equals 2x plus 2. If we solve, move the 2x over, I'm going to have 3x. Add the 4 over, I'm going to have 6. So x equals 2. Okay. This last one, quite honestly, we're already over 30 minutes, so I'm just going to skip it. But I hope that has helped. Okay, I'm going to be posting all of this, and so you will be able to get this online or in a paper packet. So thanks, guys. More to come.